Okay, good morning, and thank you for the invitation. This is just a slight organization of what I'm going to talk about, and that is Southwest England people, starting off with those people who've contributed to our understanding of the geology of Devon. Our northward migration might seem obvious, but I'll explain that. Then climate change. Well, yes, it's a modern problem, but the whole of geological history has been covered in climate change, so there's nothing new. And those people who say they don't believe in climate change are ignoring several billion years of climate change that's going on continually anyway. And then our geoscience heritage, which I do think is important, particularly to the Southwest, and particularly the UNESCO designations, one of which is obviously the biosphere is closer to you than I am. So anyway, there's Tor Bay and Hope's Nose National Nature Reserve with Thatcher Rock just offshore. And this is part of the English Riviera UNESCO Global Geopark. And we'll come back to Hope's Nose briefly later on. So the first thing that I always find is difficult with an audience that probably aren't geologists is that when we look at the natural landscape, it doesn't appear to change very much. Unless you are in a place like Sidmouth where Pennington Point Cliff keeps falling down rather dramatically, yeah, that does change. But most of us, when we look at the landscape, it's as familiar now as it was probably when we were in our childhood. And therefore, when you try to convert that into geological time rather than 70 or whatever the average is these days, you have to really think on a different scale. And I appreciate that geologists seem to have an uncanny habit of, oh, well, it was only 100 million years ago, as if everybody can imagine what 100 million years looks like. And we're all guilty, and I'll do it probably within seconds of starting the proper part of the talk. But anyway, let's kick off. And I start with this guy, William Smith. He was a practical engineer who had a very checkered history. I won't go through all of it, but I don't think he was destined for sainthood in some of his career, but never mind. He was the first person to realize that paleontology, the study of fossils, put the rocks into a stratigraphical order. And there is part of his map of the Bristol Bath area. And you can see down in the bottom right-hand corner, down here, you can see the outcrop pattern of the chalk and Salisbury Plain, which is quite recognizable. And when you look at his map of England and Wales, which was constructed, remember, in 1815, you can see the Dartmoor granite there quite happily, and you're going to see that in many of these other maps. So in many ways, the basic building blocks of what was going to be the geology of Devon was known in about 1815. At the same time, we all hear about Mary Anning and the press release about this new film called Ammonite that had so many errors in the press release, it was untrue. She didn't collect ammonites, so I don't know why they're attributing that to her, but never mind. Just to fulfill the title of the new film, here's some ammonites on the ammonite pavement west of Lyme Regis. And before you say Lyme Regis is in Dorset, this part of the cliff section west of Lyme Regis is actually in Devon. So it is part of the lecture. And of course, if you've ever walked along this beach, Monmouth Beach, west of Lyme Regis, and Lyme Regis Cobb is there, you can see this old railway line. And they used to quarry the foreshore, and they turned it into cement. There was a cement works in Monmouth Beach. And so Mary Anning had access to these continually quarried areas around Lyme Regis and just to the west. And that's why she was finding all these fossils. Where's my arrow? At the same time, and overlapping with Mary Anning, Sir Henry de la Beche lived in Lyme Regis, but he wrote about the geology of Devon, Cornwall, and Somerset. And in 1839, he wrote this absolute seminal work on the geology of southwest England. And he described the rocks of Devonshire and Cornwall as so distinctive, they were worthy of a separate geological status. And of course, the Devonian, after which was named after the county, of course, that was established in 1840, but not by de la Beche. There was a falling out between him and a couple of other geologists. So they took his idea and published it without him being involved. But he did reconstruct the seas of Dorset and Devon based on Mary Anning's fossils. And there's a cartoon, diorama, call it what you like, which shows the plesiosaurs and ichthyosaurs and fish and squid and pterosaurs flying that we see in the rocks around Lyme Regis. And this was the first ever paleontological reconstruction. He then went on to be the first director of the British Geological Survey, a really phenomenal contribution. And as I say, he got into an argument with Adam Sedgwick and Roderick Murchison. De la Beche was wrong on a couple of issues, and this was picked on by the other two. But in the end, they created the Devonian system. They suggested it in 1839, and it was formally done in 1840. So quite early in our understanding of the geology of southwest England. I'll come back to this area because up here there's a raised beach, and I'll explain what raised beaches are. And that's sitting on top of these Devonian limestones, which are full of fossils and which Sedgwick and Murchison used to define the Devonian. At the same time, Richard Owen was working, and I know this is Wiltshire. The reason why I feature Richard Owen is he was one of the founders of the Natural History Museum in London. But when he was at a British Association lecture in Plymouth in 1842, he actually coined the word dinosaur. He used dinosaur for the first time, meaning terrible lizard, but that was in Plymouth. And not many people know that the word dinosaur came from a meeting held in Plymouth. And after the meeting, he was asked to go away and write this up because it was a verbal presentation. And the organizers, the British Association, thought that, well, you know, we ought to have this word dinosaur into the literature and into the British language. And you can see where all that started. It was, you know, the beginning of dinosaur mania that many of our children still enjoy today. But that was Richard Owen. And then in the 1860s, William Pengelly, who was a Cornishman, but was living in Torquay as a teacher, then a headmaster. And two of his colleagues met on Plymouth Hoe to look at the Devonian and collect fossils from the Devonian rocks that form the headlands around Plymouth Hoe. And they decided that they would form the Devonshire Association, very much modelled on the British Association. And the first meeting was held in Plymouth, and the first proper conference was held in Exeter in 1862. And you can see there the typical view from Plymouth Hoe of Mount Edgecombe to the west, Drake's Island out in the middle there, there's Drake's Island again. And we're looking out down Plymouth Sound, which of course is a special area of conservation, and it has been proposed as Britain's first marine park. Not for what you can see, but for what's underneath the waters. And I think I overheard in a conversation Keith Hiscock, and of course Keith has published a whole series of papers and books on the animals and plants, algae that live below Plymouth Sound. And then we come to the turn of the century, and there's a map, a geological map of Torquay, which was created by W.A.E. Usher, and that was in 1903. And Usher described many of the areas of southwest England, particularly including Torquay, but he also mapped Plymouth. He also mapped the Bideford area and parts of the Tean Valley around Exeter, and in particular the Exeter area. He worked for the British Geological Survey, and 2020, it's the centenary of his death, and he's commemorated by the Usher Society, which is our regional geological society. And down in the bottom corner there, you can see this beautiful filigree appearance of native gold that comes from the very end of Hope's Nose, a gold vein that the local authority and Natural England fight to stop people removing by chainsaws and everything else. The Natural History Museum have now largely moved it all to the museum in London, so there's not much of it left now. So that takes us to the beginning of the 20th century. And as you can see by this detailed geological map, we knew an awful lot about the geology of Devon. It really was quite well known, mainly thanks to Delabèche and Usher. But the problem was a lot of it didn't make sense. And when we look at the geological map, and this is a simplified version, you can see the Dartmoor granite there, which was on Smith's map in 1815. You can see the Devonian rocks, these dark grey and purple, in North Devon and South Devon. Slightly younger Carboniferous rocks, these yellowy colours, in the middle of Devon. And then these younger rocks, these Permian sandstones in grey, and then Triassic sandstones in brown, and then the Jurassic in blue and the Cretaceous there in green. You can also see this major fault that runs right through the county. There's a couple of others running through here, and they are formed when the Alps were being created further south in Europe. So they're quite young features compared to the rest of the map. But although we knew the distribution of rocks and we knew what they were doing, we really didn't understand how they held together. And that became apparent in 1912 when Alfred Wegener gave a lecture on the origin of continents and oceans at the Senckenberg in Frankfurt. The paper was published, the one you can see there, in 1915, which is 3 years later. Wegener was suggesting that the continents had not been where they are today through geological time, that they had moved. Now, the geological community immediately completely lampooned his ideas because he could not answer the question, why did the continents move? He was suggesting they all moved around, but he couldn't suggest how. And these are sort of not his maps, but these are conversions of some of his maps. And if you go to the bottom left, here you can see 400 million years ago, Devon, south of the equator. And then about 300 million years ago, crossing the equator, and then gradually moving northwards through the Jurassic and Cretaceous, and eventually ending up at 52 degrees north at the present time. So in around about 400 million years, Devon has moved from being south of the equator to where we are today. And that, of course, leaving aside how it does that, that of course explains why in Torquay we have these beautiful coral limestones, because those coral limestones were forming where we see coral reefs today, just south of the equator, like the Great Barrier Reef in Australia. When we crossed the equator, which is here, in the Carboniferous, we had complete forests, tropical rainforests, and that's of course the coal measures of Britain and Northwest Europe. And then we go into desert environments in the Permian Triassic, roughly the latitude of the present day Sahara. And then moving northwards, we end up in our present position. Now, of course, that begins to piece together the history of what the rocks were that William Ussher was describing. But he hadn't been able to understand why he had these coral limestones in Tor Bay. But this now gives us a method of understanding that. And this is the history of the continents moving around. Now we know that it's not the continents that are actually causing the movements. It's the creation of ocean floor. And there you can see a rift between South America and Africa, which opened up about 100 million years ago. And it was the creation of that ocean floor between these two continents that made them move apart. And of course, today we are still moving. We are moving northwards. We're also moving slightly westwards. The good news is, of course, the fact that New York and Biddeford are moving away from each other at 4 centimeters a year, so that if President Trump gets elected again, we'll be further away from him than we are now. And the rate of movement of you folks in North Devon from New York is around about 4 centimeters a year. And I always liken that to the rate your fingernails or your toenails grow. If you think when your finger or toenails grow, you cut a bit off. Well, if you add up all the cuttings over a year, that's roughly how far New York is further away over the course of a year. Now, other places are moving slightly faster, but that's our position here. The other thing is that if we now use this model, we can see that the cold, warm temperatures actually make sense. That, you know, we can actually piece these together considering where the world was in terms of continental configuration. So when the Antarctic moved on top of the South Pole, that's why we headed into a glaciation. And it was when in the Permian there was continents over the South Pole, we had this glaciation in this interval. And so it begins to make a lot of sense. But of course, this curve, which you can see running up through here, is apparently not getting any warmer in terms of the average. And yet the luminosity of the sun is getting greater. And the temperature radiated from the sun has gone up by about 30% through this time interval. So why is the Earth not warming up to the same degree? And the answer is that the climate is regulated by the plants and animals on the Earth. And this is where James Lovelock came up with the idea of Gaia hypothesis, that biological intervention is what is actually helping in terms of, sorry, it's my phone going off. I've just killed it. So in other words, instead of the temperature going up, it has been stabilized by plants and animals through time. And that's really quite an interesting way of looking at paleontology. So if we go back to our Devonian and the coral reefs that William Usher described, here's Devon, just south of the equator. Here's the geography of the time. And we had coral reefs that extended from New York State through southwest England into Belgium and into the Rheinische Schiefergebirge in Germany. It's almost the same length as the modern Great Barrier Reef. And so we, using Wegener's adapted model, because we now know a lot more about it than Wegener ever did, we can actually reconstruct our environments. And so when we take the evidence from the quarries around Torbay and the beautiful limestone exposures here and on Hope's Nose, which are actually punctuated by volcanic eruptions. Here's the volcanic ash. And when you look at the thickness of that ash, it really was quite an eruption, because wind-blown ash falling into the sea doesn't normally form thick layers like that. And when we try to draw cartoons, we can see that in the Plymouth area and in Torbay, we have these shallow seas with our coral reefs. And we have a series of volcanoes running through. This is just to the west of Newton Abbot, near Chipley, where there's underwater volcanoes. And these are probably where the ash in Torbay came from. The interesting thing is that this cartoon says deep sea. Well, I don't know that it was as deep as some people imagine. And I tend to get into a conflict with people about that. And that links to ocean acidification. And I'll come back to that. But then in North Devon, you can see that we're in a shoreline situation, and then the mountains of Wales and Scotland. But what was happening in this wonderful little scenario here was that a rather large continental mass around in Brittany was migrating northwards. And if you put your tablecloth over your kitchen table or dining room table and put a couple of books about a meter apart and then move those books towards each other, what you do to the tablecloth is you create a whole series of ripples in it. And here's some of these ripples. That is a fold, an enormous fold. Here are some folds within these rocks. And if you do the model of two big books, the tablecloth, you'll be able to produce these sorts of things quite happily. And when we look at the map of southwest England, we can see that the two continental masses move together from a north and south direction. And so all the rocks, these boundaries here, between the dark red and the pale red, or between the yellow, or here with the green, they're all round about east-west. And that's not a random distribution. That's a distinct pattern which relates to the movement of continents. And of course, what we see on a local scale are these large folds, these major fractures. This is a huge thrust fault. But these rocks here are upside down, but if you turn them the right way round, they follow back over and back over upside down again. So we can see that the continental movements control the landscape. And if you drive around the county of Devon, you'll notice that many of the features are east-west, or approximately east-west. You can also see that Dartmoor granite, which came after the folding, cuts through the whole thing. The boundaries run across, and Dartmoor punches its way through due to melting of the crust, and actually distorts in some ways the folded rocks. And that's how geologists put things in time order. We see things that are affected by one and not the other, and therefore we can work out relative timescales. Now, these mountains that were created by all this folding were probably 2,500 to 3,000 meters high, really quite large mountain chain. And it used to be called the Hercynian. We now tend to use the term Variscan orogenic belt. And so the landscape of Devon is very much controlled by these east-west features that we see running across the county. But the rocks that came later, these orangey brown things, you'll notice they cut right across. So they're later. And these cut across and follow the structures. You can see it's actually cross-cutting the boundaries here. And it's cross-cutting the boundaries there. So again, we can place these in a chronological order. And when we look at where we are, this fold mountain belt was sitting pretty well within 5 degrees of the equator, so modern day Sahara. And when we look at the rocks in East Devon or Torbay, what we see are these wonderful red sandstones with these huge pebble beds. And if you imagine you've got a range of mountains which are several thousand meters high, blocks of rock are just going to be cascading off these. And of course, being near the equator, it's very much an equivalent to the modern Middle East. Now, when they were doing the signboards around Torbay, I got into terrible problems because they wanted these to be the red rocks, and the artistic director actually turned the sky red. The whole environment was red. And I had a rather falling out with them over this, because if I look at these rocks in Torbay, these are, and then go and do some field work in the Oman Mountains, I can see pebble beds and structures which are exactly like those in Tor Bay. And here's a whole cliff which is really very typical of these things that we see around southwest England. But these rocks are not red. So what's going on? Well, the answer is that if you dig a big hole in the Oman Mountains, you will actually get down to red rocks. Because what happens below the surface is that any iron minerals, whether they get chemically altered and they rust. And so gradually with burial, these Pleistocene waddy deposits turn red. But as you can vividly see here, the sky in the Oman is not red, nor are any of the rocks. Hence my falling out with the artistic designer. But never mind, we can see what these things are like. I should say that the day after this was taken, I slightly wrecked this vehicle by driving into a wadi, not realizing that there was a flood coming down the wadi. There'd been a thunderstorm high in the mountains, and this wall, which was about 1 meter high, of boulders and a little bit of water came rushing down the wadi and completely snapped the wheels off that Land Rover, which didn't go down very well with the owner of the Land Rover, but never mind, the joys of field work in the Middle East. So these rocks here, these Permian Triassic red sandstones, which so characterize the area around Exeter. You know, if you look at the fields, the red soil, even the sheep that sit on the grass are usually red as well in some places. And these are such a characteristic feature of the landscape of Devon. Now, when we extend further east into East Devon, these are not Permian red rocks, they're Triassic, but you can see here a cliff of the area around Ladram Bay, and Sidmouth's just round the corner. And so these quite thick red sandstones are still picking up this iron oxide stain, and the farmland has these beautiful red soils. But in these deserts, there were some plants. We've got evidence of spores and pollen, and there must have been vegetation because there are animals feeding on it. And this is a rhynchosaur fossil. There's a foot down here. There's some ribs up here. The only thing missing is anything connected with the skull. So we think this poor rhynchosaur fell into a river, which we know from the sediments was running west to east through Ladram Bay. We've got a river in these rocks, which was roughly the same size as the River Thames. And this poor little rhynchosaur must have fallen in and its head snapped off its body, but never mind. We do find these rhynchosaurs all along this coastline, as well as the things that would have eaten them, and there were fish in some of the rivers. So we do have a pretty good community. So when we've been looking through this history for this early part of the record up to the Permian and Triassic, I mentioned the fact that in the Devonian, was that sea particularly deep or shallow? Well, this is a graph of carbon dioxide. Now look at the carbon dioxide. It is this is where we are today. And everyone says, oh, carbon dioxide's a problem, it's causing climate change. Well, this is where we are today. Look at it in the Devonian 400 million years ago. And even in the Cretaceous, the carbon dioxide in the atmosphere was between 8 and 12 times what it is today. And of course, if you had that level of carbon dioxide in the Devonian atmosphere, then the seas would have been really quite acidic, using ocean acidification as a model. And of course, that would have meant that I don't think those seas were particularly deep, because you find calcareous fossils in the sediments, and they could not have survived with that level of ocean acidification. So why did this curve come down? Well, vegetation developed on land. And then during the Jurassic and Cretaceous, the plankton developed in the oceans and brought it down again. So where we are today, our atmosphere is controlled by plants on land, plants under the sea, and the plankton. And so the carbon dioxide in the atmosphere is controlled by life on Earth. But of course, sadly, we do the reverse to many plants and animals. We breathe in oxygen and give out carbon dioxide. And that means that with how many billion people on the Earth at present, we're working against what all the other animals and plants are doing in terms of generating an oxygen atmosphere and reducing the carbon dioxide. And in the Cretaceous, there's the same curve. In the Cretaceous, when you look at the rocks around Beer and the chalk cliffs here, you have these wonderful plankton. Now, each of these are probably 1,000th of a millimeter across. That's a modern one. These are the fossil ones that formed in the chalk. And these are controlling the carbon dioxide in the atmosphere. These are fixing the carbon dioxide, and really enormous quantities. When you think that this cliff in Beer and round the corner at Beer Head is probably 1,000 meters thick, and it's made up of things that are fractions of a millimeter. But of course, the climate was much warmer then. This is the paleogeography. Spot the land. The nearest shoreline are the mountains of Wales or the coastline of Sweden. So that's our history. Order comes out of chaos. But when we come up to this record, you notice these fluctuations. Well, our present day climate is controlled by carbon dioxide in the atmosphere. Absolutely. How do we know what's going on over time? And this is 400,000 years. Well, you take a stick of ice from a core in the Antarctic. And when you do that, what you find is that you get temperature changes that you can measure. You can measure the carbon dioxide level in the atmosphere, and we only have 300 parts per million. When you look at how it fits together, it quite clearly shows that carbon dioxide and temperature are intimately linked. If you're President Trump, you believe that it's the temperature that's causing the carbon dioxide. If you're practically everybody else on the planet, you believe it's the carbon dioxide causing the temperature. But then, of course, our modern, and there we are in 2012 at 390 parts per million. As Greta Thunberg would say, in 2020, we are at 412 parts per million. And so that is the difference. And this is the so-called hockey stick, where you go from an average that had lasted for thousands of years at one level, and we're now flying high quite above that. And we see that record. If we take our record through time, we can see that our raised beaches occur when sea level and climate was warmer. And we can see that in the way that in cave systems, we have mammoths and reindeer, and we have hippopotamus and in Honiton, and all those sorts of animals that are the warmer intervals. And equally well, we have the colder intervals, which represent the glaciations, 1, 2, 3, 4 glaciations over the last 500,000 years. And we see this record in caves all around Tor Bay, as well as the show cave in Kent's Cavern. We can see this in all these other caves, particularly under Berry Head. Now, huge arguments about what these oyster beds and the raised beaches are like. There's some really fruity language between some experts and Arthur Roop Hunt, and they're all in a free download from the Devonshire Association transactions. And this is sea level about 125,000 years ago, 7 meters higher than today. So, comfort break, and then I'll describe some of the landscape very briefly. Is that okay?
Yeah, that should be okay.
Mute your mics, everyone.
Well, okay, just a brief mention of the Jurassic Coast, because it is an important part of our record in Devon and Dorset. And it's because of its outstanding universal value. That's the key definition of a World Heritage Site. Just the same as the Cornish and West Devon Mining Heritage Site. It's all connected with outstanding universal value. And on the Dorset coast, we obviously have this record from Exmouth round to Swanage. There's the red rocks at the western end at Exmouth, and then the chalk cliffs at the other end at Old Harry Rocks. And so that's a complete coastline, with Mary Anning quite clearly contributing to our understanding of the fossils that she collected both west and east of Lyme Regis. Sadly, the quarries that used to take away the foreshore that Mary collected from had to be stabilized, and that cost £22 million, largely human inflicted by quarrying away the foreshore. And some of the fossils she found are really amazing. Here's a fossil squid, and there's its ink sac that it would use to blow ink into the water to escape. And there's the arms covered in hooks like these hooks here. This is a new specimen with the ink sac. The arms, which you can see lined with hooks. Absolutely beautiful specimens collected today from the same localities that Mary Anning used. And this is from Lyme Regis, again, the cliffs just to the west of Lyme Regis, which are actually, as I said, in Devon. And here's an ink sac from a squid, and here's the arms of the squid actually holding a fish. And the head of the fish is battered where the squid has bitten chunks out of it. So we can see life and death really beautifully. And we can see on the coastline these beautiful brittle starfish. The only problem is that fossil collectors are taking saws to the whole area. And you can see where all these beautiful specimens have been carved out. And that's a real problem that we've got to deal with. And then the coastline goes off into Dorset with some beautiful scenery and geology, which obviously isn't part of Devon. There's a beautiful ammonite. Here's a fossil tree. and here's a fossil soil that the tree was growing in. So absolutely amazing contribution to our heritage. And we get things like these beautiful ichthyosaurs preserved, collected by Steve Etches here. And so we built up this fantastic record, but the Jurassic Coast has all sorts of pressures on it, which I won't run through those at all at the minute. Geoparks are the same in a sense that they're a UNESCO designation. And this is Torbay, Berry Head. And of course, the shape of Berry Head is actually a quarry. This is all a quarry face. It's not a natural headland. You can see the benches in the quarrying there. The other thing you can see is that the hilltops throughout this area and almost throughout Devon are all at about the same level. And that's because when we look at sea level through time, if we go back and think of this interval here about 8 million years ago, this is what Devon and Cornwall would have looked like. And we can see how those hilltop surfaces developed through time. In other words, those hilltops that we see around Torbay and see around central Devon and all around Cornwall are actually geological features going back in some cases 20 million years. And they're preserved. Okay, they've been cut through by recent rivers, but you can still see those surfaces. And of course, if climate change extends further forward and sea level rises, we'll be returning to some of that coastline as it was then. Of course, we do get these people pontificating on this climate change, Nigel Lawson and our dear friend. And you get these most amazing literature put out by people who can afford to do it. And they just portray the fact that the scientists have completely lost the plot, which I can assure you we haven't. So when we look at the Earth system and how the landscape has responded to that Earth system and how climate has changed life on Earth, this diagram here is one that I drew in 2000. And I drew there that these are extinction levels through time. And in 2000, well, actually, I drew the graph in 2005, but in 2000, 30% of the life on Earth had become extinct. So all this Greta Thunberg and Extinction Rebellion, the scientists knew all about this in 2000 and 2005, and we were already plotting the extinction rates that were happening. Now, when we look at Earth system science, one of the things that came up was the European Landscape Convention, which was written in 2000 and ratified eventually by the whole of Europe in 2004. And I should say that although it's the European Landscape Convention, this is not the European Union. This is the Council of Europe. And it was the Council of Europe that wrote the books on the conservation of European wildlife. And despite the fact we've left the EU, we are still part of the Council of Europe and therefore still signed up to the European Landscape Convention. And when we look at landscape, we have to think of place, in other words, the natural features, in other words, the geology, geomorphology, soils, and the animals, plants, and the climate. We have to look at cultural things and societal things. And we also have to look at perception of what we see, and what might look nice to one person might not look nice to another person. So when we look at the landscape, it's very subjective on our preferences. And we know what we like when we see sounds and smells in the landscape. And it's all part of understanding landscape. Now, geology of Devon obviously is the bedrock. But when we look at national character areas, and this is the map of Natural England's natural character areas, the map is almost, well, it's not the same as the geological map, but there's Dartmoor, North Devon and Exmoor is this area. This area is the red rocks of the Permian and Triassic. And so these national character areas just map onto the geology, which is what you'd expect. So in the southwest, we have these national character areas. 150 is Dartmoor, and you can look these up online and read about the features. 151 is South Devon, 158 is 159, sorry, is Lundy, and then we have the Black Downs, the Vale of Taunton, and Exmoor. Now, each of these national character areas reflects the geology, trees, woodland, agriculture, history, settlements, everything that goes into the perception of people and the landscape. And of course, when we look at landscape, here's the chalk plateau around Beer and Branscombe in southeast Devon. And you can see there this huge landslide that's slipped out of the cliff there. You can see that vividly portrayed there and visible from the air. And when we look at the landscape, particularly in a county like Devon, if you go to Beer, you'll notice that many of the cottages are built out of the flints from the chalk, or Beer stone, which was quarried nearby. And it was the quarry managers that had Beer stone houses. The slightly poorer people had the flint houses. And then in mid-Devon, we have the cob houses, which are built of the red clays of central Devon. And then the red rocks of the Exeter area in Cathedral Close. And then many of our building stones are particularly characteristic of churches. And we can look at the stones within buildings, within walls, and it reflects the local geology. And I always remember going into one area, which isn't in Devon, but there was a house, a modern house built completely of flints. And you had to ask why it had been given planning permission, because there weren't any flints in that area. So it was totally out of keeping with the natural environment. So these characteristic landscape areas are part of what we understand. And they're part of a huge body of conservation legislation. And we get these sites of special scientific interest to preserve scientific value, national parks, areas of natural beauty, outstanding natural beauty, special areas of conservation, special protection areas for birds like the ex-estuary. And we now have marine conservation zones based on the experiment around Lundy of a no-take zone. So these are important bits of conservation within the southwest. So if we take Dartmoor, for example, that obviously picks up Wistman's Woods, it picks up the typical Herdwick stone buildings in Tavistock and Herdwick stone in the bridge here, Yarner Woods in East Dartmoor, and of course the Tors on Dartmoor are all part of our wonderful landscape that are picked up by these national character areas. Some of them work better than others. Obviously, Dartmoor is one that works because it's got a national park, it's got a national park authority, and it's a cohesive unit. The South Devon one, which includes South Hams, Torbay, the city of Plymouth, clearly doesn't hang together because it's made up of too many different areas. But I mean, okay, even the South Devon one with Torbay, with Plymouth Sound, with the Tamar Valley, with the Calstock Viaduct here, there are parts of it which we would recognize as important aspects of the landscape, even though the character area doesn't really hang together too well. Now, when we look at UNESCO sites in Devon, we have Cornish Mining Heritage, which is a cultural site, the Jurassic Coast, which is a natural site, Broughton Borough's Biosphere, which is a Man and the Biosphere Programme site, and we have the English Riviera Global Geopark. So all these landscape features like Broughton Boroughs, the Dorset Coast, the corals of Torbay, and the mines of Batalic and places like that, they're all part of our UNESCO recognized landscape heritage. And of course, we do have our national parks and areas of outstanding natural beauty, which are managed by Natural England and which draw attention to the great value. And when you look at Devon, we have more designated sites virtually than any other county in the UK. And we should reflect on that and be proud of it. National nature reserves all over the place, a whole host of national nature reserves, including things like Slapton Lea, and we also have the wildlife trusts with other sites, not officially recognized at the national level. But all these features, it's rather interesting that Slapton Lea regularly gets in the news because the road gets breached. And the question is, do you keep rebuilding the road, or do you let sea level change move the barrier beach up against the coastline and remove Slapton Lea, which is what will happen unless you intervene and do something about that road. So preserving a landscape is an interesting debate on whether you let nature move forward or whether you try to hang on to what you've got, which inevitably leads to more and more, shall we say, concrete structures to try and protect the area. So you have to be very careful, and it's an interesting debate about how much you want to hang on to today's landscape and environment, or whether you let things modify through time. So landscapes have to be conserved, protected, managed, and you end up with a question of, you know, are we dealing with a landscape that's basically gardening? In other words, we're completely changing it. And there are very few places like Wisman's Wood which are left as a completely natural area. Farmers and countryside managers have got a major role. And I don't want to mention Brexit because that's a sure conversation killer. But what happens to the landscape as a result of post-Brexit farming is an important issue. So Devon's geologically quite diverse, it's quite unique. It's got the only geological interval of time that's named after it, the Devonian. And we also have this beautifully conserved, managed and protected landscape. Unfortunately, just before English nature disappeared, the state of nature showed that all is not well. And if you go on the Devonshire Association website, you can sit through 4 or 5 talks on the state of today's nature, and that's free of charge. It's just on the Devonshire Association website. And another document which I helped produce was looking at natural foundations, how the geology of the landscape and the landscape itself are all part of the same system. And that's where I'll end with the advert for the Devonshire Association website, and for a plea to understand geology and geodiversity when you look at the landscape and hopefully enjoy it.